Hello, children. I thought I'd give you one on Bernoulli's equation example. So here's one out of the book, actually. Ship in a lake. The hold is the interior space beneath the deck. Blah blah blah. The hull has a hole in it, which is below the water line. All right. So we have a situation that looks like this. Here's the hull of the boat, something like that. Here's the water line. Goes to here. And then there's a hole right there. I'm going to make that hole a little smaller. There we are. And let's see, this is 2 meters below the surface. We have an area of the hole. And we want to know the volume of water per second. Now you might recognize this, volume of water per second. What quantity are they talking about there? Yeah, that's right, it's Q. Q equals question mark. So notice we have an area, we want a Q, so we're going to have to do AV. The question is, at what speed does water leak into that hole? Okay, so here's the deal. This is a Bernoulli equation question. How do you know? Well, I know because I see different heights. I know because it involves a speed of water, a speed of a fluid that's rushing into this hole. All right, and we can assume that there's a speed out here. Any guesses as to what that speed is? Well, it's 0. It's not really 0, but we're actually kind of saying, how quickly does the surface of the water drop? Well, the area of the ocean, whatever this thing is so much, the surface area is so much bigger than the area of the hole that the effective velocity of the surface of the water is 0. The question is, what's this speed in here? So we have a thing with heights. We have a thing with different speeds. That to me screams Bernoulli's equation. All right, so I'll write Bernoulli's equation. P1 plus rho GH1 plus 1/2 rho V1 squared is P2 plus rho GH2 plus 1/2 rho V2 squared. Arbitrarily, let's call this area 1. Let's call this area 2. Let's see. Okay, some things we can do. For sure, if area 1 is inside the hull, or really, sorry, here's height 1, we can get rid of that we can not get rid of it, but call it 0. Okay, and we can also get rid of our 1/2 rho V2 squared. All right. Could you tell I just hit pause after the first time I said, I didn't know what to do next. There's a couple ways you can go about this. One literally is to call location 2 right where we have it drawn. All right, if you do it that way, we have a pressure at location 2 that's actually equal to just atmospheric pressure, right, at the surface of the water. The other way to do it is to say that location 2 is right here, right, really at the same height. We kind of say, here's 1, here's 2, right? And if they're at that same height, we can get rid of the heights. All right, I'm going to go ahead and do it that way. All right, we'll say they're both at height 0. All right, now the deal is, if we approach it this way, well, hopefully we can tell that pressure 1 is atmospheric pressure. And the reason that is because it says in the question, here it is, the hold is empty and is open to the atmosphere. That tells us the pressure at 1 is atmospheric pressure. All right. Well, the deal is, you know what, I'm going to go back and do this in green so it shows the green solution. So pressure 1 is P ATM. Well, in this case, pressure 2 is below the surface of the water. All right. So we have to do a P above, which is atmospheric pressure, plus rho GH. All All right, how far below the surface of the water are we? All right, that would be that 2 meters. All right, so notice that even though we got rid of both heights here, saying 1 and 2 are at the same place, we end up putting that rho GH back in there. All right? Now, the other way to do it is we do it the way we have it labeled in red, where 1 is inside the boat, still at that, at this height, and 2 is at the surface of the water. If we do it that way, well, pressure 1 is atmospheric pressure. Pressure 2 is atmospheric pressure, right? They're both in the air, right? If we say pressure, location 2 is at the surface of the water, okay? But if we do that, notice that we can actually get rid of both of these pressures because they're the same pressure. But if location 2 is at the surface of the water, well, we'd still get rid of location 1's height, call it 0, but now we do have this height 2. Okay? Now, if we go back to solution 1 here, if we have a PATM for both places, well, we can really get rid of the PATM here and the PATM here in pressure 2. This would just turn into, that's what's left over, rho GH. All right, same exact thing as we do down here in this solution. I'm not sure this is clearing it up or making it more confusing, but the short story is no matter which way you do it, you end up doing the same exact thing. Okay, so I'm going to press forward with this solution here. Well, it's not. It's the one in red. I'm going to press forward with this solution where we're saying that location 1 is in the boat, right, right here, and location 2 is at the surface of the water. Both pressures are the same, but height 2 is 2 meters above height 0. All right. Now, no matter what, we definitely said we can get rid of velocity at 2. All right. So all we're left with is, a fairly simple expression here for velocity. We have 1/2 rho v1 squared is rho gh2. All right. Get rid of our rho's, and we have that v is 2 gh2. That gives me a value for V of 6.3 meters per second. If we go back to the beginning, what we really want to know is our value. I'm going to take this up here. We want to know this value Q, the rate at which volume, well, really the volumetric flow rate, which is A times V. All right, so that gives us Q 8.0 times 10 to the negative 3 square meters. I didn't get the squared in here. Times 6.3 meters per second. 8e negative 3. So that's a Q of 0.05 cubic meters per second. There's your answer. Okay, so a couple of things with Bernoulli's questions. First, how do you recognize them? Well, it's got to be a case where, let's look at the main terms. Let's take this again. Let me clone this. Here's Bernoulli's equation. Okay, it's questions like this have to be a case where, you're trading something like, a high pressure in one area for a high speed in another, or a high, height of water or a fluid in some place to a high speed of water in another, or, a high height of water in one place to a high pressure in another. So you have to look for, what's the fluid doing in one location in terms of what pressure does it have, how high is it, how fast is it moving, and what changes as you go to a different location. Is pressure different? Is height different? Is speed different? All right. If those things change from one place to another, Bernoulli's equation is the appropriate way to solve. All right, now notice, just like we've said before, that Bernoulli's equation has the expression for what we call pressure at a depth. All right, and those equations just look like this, or those examples look like this: P above, P below equals P above plus rho GH. That's what we call a static fluid statement, and static means not moving. Notice that that's the same thing as Bernoulli's without the terms for velocity in there, because the fluid's static. And we've also said that we've taken one of the rho GH's out because we assume that one height we'll just call height 0. All right, so even in cases where things aren't moving, it's actually still appropriate to use Bernoulli's equation and just drop out the 1/2 rho v squared terms. All right, you know, we're probably a little more used to in static cases just using that expression for pressure at a depth, but they come from the same place. Okay, hope that helps. See you soon.